Monitoring tests were carried out by Brian Webb and Martin Smith, senior scientists of the Building Research Establishment, from Monday the 10th of August to Friday the 14th of August 1998. The purpose of these tests was to determine the effectiveness of the Monodraught wing catcher system under the most arduous summer conditions, but also to simulate other conditions throughout the year. The BRE erected their own weather station externally so as to carefully monitor wind speed and wind direction throughout the duration of the tests. The two lecture rooms were created in the building, which originally housed the university's mainframe computer system, which, as can be seen, the building has very few windows or door openings. These lecture rooms were originally served by the old air conditioning system, but due to its age it was very noisy and unreliable and was eventually decommissioned 3 years ago. Since that time, the lecture rooms have suffered from severe overheating during summer months, and the four Monodraught wing catcher systems were selected to overcome the problems of inadequate ventilation and overheating that had been experienced. As can be seen, there is a vigorous downwash of incoming fresh air from ceiling level, and an equally vigorous venting of warm stale air that rises up and passes out through the Monodraught stacks at ceiling level. The charts show a variety of conditions that were measured to determine this air change rate that was being achieved under these varying conditions. Firstly, as you can see, when the dampers were closed, or indeed when the whole system was sealed up, the air change rate was approximately quarter to half an air change per hour, irrespective of outside wind conditions, and this would be due to normal building leakage. The air change rate, however, created by the Monodraught wing catcher system, varied from just over 1 air change per hour, with a very low wind speed of 1.5 meters per second, up to nearly 5 air changes per hour when the external wind speed was 4.5 meters per second. Bearing in mind that the monitoring devices were positioned in the very extreme sides of the lecture theatre, and bearing in mind also that these measurements were being taken when the external temperature reached more than 29 degrees C, the air change rate measured is extremely satisfactory. The benefits of nighttime cooling associated with the wing catcher were also measured, and the graphs show 3 conditions. The upper green line, taken in room G111, was when the systems were sealed up with polythene and would relate directly to a similar condition when the building is closed up overnight. Similarly, it would relate to a condition when there was a building not served by the wing catcher system. It can be seen from the graph that the temperature level immediately rose to approximately 24 degrees C when the ventilation from the Monodraught system was closed up, and then dropped from 24 degrees C to just below 20 degrees C overnight. The bottom blue line shows the external temperature, and the middle red line shows the beneficial effect of cool night air plunging down from the Monodraught wing catcher, as can be seen. This lowers the internal temperature by approximately 3 degrees as compared to the closed-up condition above. Not only does this reduce the temperature, but this clean fresh air also leaves the building feeling pleasant and clean when people arrive at 8:30 in the morning and when the temperature is just above 18 degrees C. The building was not particularly designed to benefit from night cooling, since the suspended ceiling and plaster walls are not conducive to benefit from nighttime cooling, but nevertheless a reduction in internal temperature of 3 degrees C under these circumstances is a very beneficial achievement. Day 2 of the testing was reputed to be the hottest day of the year. This was on the Tuesday. There was very little wind movement externally, and as can be seen, the downflow of air was less vigorous than on the first day. The graphs that we have seen show that on this day the wind speed dropped to approximately 1 meter per second, but still, nevertheless, the film shows the warm air in the building rising and venting up through the passive vent section of the Monodraught system and being replaced with cool air flowing down from the outside. Under these conditions, when the doors to the outside were opened, the Monodraught system immediately changed its function, with cooler air entering the building from the outside through the doors, and the Monodraught system is then acting purely as a passive stack, with all 4 quadrants taking air out of the building. This situation would be typical of a normal building when windows are opened, creating good cross-ventilation, with a flow of fresh air passing across the building and venting up through the Monodraught stack at ceiling level. This, of course, is the most natural course for air to pass. It can be readily seen, however, that the unique advantage of the Monodraught system is that once the windows are closed, the system still continues to operate with clean, fresh air coming in and passing down from ceiling level, and the stale air being vented up the opposite side of the Monodraught system. On days 3 and 4, the wind picked up to approximately 5 meters per second, and as can be seen, the downflow of air was more vigorous. As can be appreciated, this wind pressure to one side of the Monodraught system is clearly blowing in cool, fresh air from the outside. This tends to slightly pressurize the building, encouraging the outflow of air up the opposite side of the Monodraught stack. The BRE report notes that during the course of days 2, 3 and 4, the outside temperature level during the time of the test, which was from approximately 11 o'clock in the morning to 3 o'clock in the afternoon, ranged from approximately 20 degrees C to 29 degrees C. In fact, the highest temperature level recorded during the test was 29.5 degrees C on the Tuesday. Under these high temperature conditions, it's very satisfactory to see a constant flow of fresh air into the building and stale air being exhausted. On Friday the 14th of August 1998, members of the press, architects and consulting engineers were invited to witness the performance at first hand, and again similar conditions prevailed. The question asked from one of the visitors was that since it was very warm outside, it was approximately 27 degrees C, there was a definite perception on the interior of it not only feeling much fresher than other parts of the building, which were not served by the Monodraught natural ventilation system, but there was also a definite perception of a cooling effect taking place. This cooling effect is, of course, created by the vigorous downwash of incoming air, even though the outside temperature was still around 25 to 27 degrees C. Although the internal temperature, as shown on the detailed report, was also in the same temperature range, the perception of vigorous flow of fresh air has a cooling effect on the people in the building and is very beneficial all round. Clearly, in mid-season, the dampers would start to close under the temperature sensors to limit the number of air changes, and indeed, in winter months, these dampers would close up to approximately 95% closed to still allow an air change rate of approximately 1 air change per hour. Egg crate grills are used to ensure a rapid downflow of fresh air with a minimal resistance on the airflow rate, but a wide range of ceiling diffusers could also be used. In conclusion, therefore, we are very pleased that these tests carried out in what turned out to be the hottest week of the year in August prove that the Monodraught wind catcher system does indeed perform in a very satisfactory manner despite very high external temperatures. If it performs so well under these most arduous conditions, then clearly it can be seen that other times of the year it will also perform just as well.